Manon is going to introduce our speaker today. I just wanted to mention that we have something planned for the end of the meeting, so don't leave the meeting right away. All right.
All right. Thank you, Narad. Welcome everyone to this last talk of 2020. Today we welcome Sébastien Labbé from L'Abri in Bordeaux, who's going to talk about a characterization of Sturmian sequences by indistinguishable asymptotic pairs. Please, Sébastien.
Okay, thank you, Manon. Thank you, everyone. Thanks for organizing this great Monday seminar. I like it very much. So today I'm going to present yet another characterization of Sturmian sequences. So I was happy to work on this with Sébastien Barbieri and Stepan Starosta. So it was a question that Sébastien brought last year while during his stay in Bordeaux. So it was a lot of equation of words, like words overlapping. So I thought that might be a nice question to look with Stepan, who knows also what he calls the overlapping hell in combinatorics on words. So as you see, we decided to choose another ordering for the name. Instead of the lexicographic order, we choose the increasing order for the number of accent in the name. So it's much simpler like that because it's 1, 2, 3. So this is a suggestion for a new model for the ordering. So let us start. So the talk is divided into 3 parts. So in the first part, we will recall notion that many people know about Sturmian words, including mechanical words, Christoffel words, and the Pirillo's theorem. Then I will introduce terminology, so starting with symbolic dynamics, but also well, asymptotic pair, I think it's well known, but new notions, let's say like pattern discrepancy, or the notion of indistinguishability of asymptotic pairs. And then we will present 3 theorems, and I will try to present the idea of the proofs with 1 or 2 slides, or mainly the main point or main interesting point of the proof for each of the results. So as you have seen on the previous slide, the result is available on the archive, so you can read the proof or the details on the paper. So let me start with the mechanical word. So mechanical words is a notion. This notion is present in the early work of Morse and Hedlund, whose title is Sturmian sequences. But in the paper, they mentioned the idea of mechanical words, which was also reused in other books like Lothar more recently. So let me define this. So here I take alpha, any number between 0 and 1, including 0 and 1, and including the rational as well. So either rational or irrational number. And then I define 2 configurations, C alpha and C alpha prime. Which I will call the upper mechanical word and the lower mechanical word. So these are the configuration defined on all of Z, so the non-negative and negative integer, like this. So of course, this is defined, is closely related to the line passing through the origin of slope alpha, which is the black line here. So this is a line in the Euclidean plane. And if at each integer position, you evaluate, then you get some value. So the point here. So this is a real value. So you can take the floor or the seal of that, and that gives you 2 paths that are shown in blue here and sometimes in red, that are just above or just below. So making the link between the integer point just above or just below. And between 2 consecutive integer, n and n plus 1, you can compute the difference. And the difference in this case, since alpha is between 0 and 1, will be always 0 or 1. Okay, so either you go straight or either you go up. Okay, so This difference is computed in this formula. So either here you take the seal part or the floor part. So most of the time, these two values will be, the difference here will be the same, except when either alpha n or alpha n plus 1 is an integer, because the seal and the floor of an integer is that integer. So in that situation, the upper and the lower mechanical word are not the same, but then it's always like that. So either it's moving up by, sorry, I pressed the button, 1, 0, or the other one will be 0, 1. Okay, it's always like this. So this is if the slope is rational. If, of course, if the slope is irrational and you start at 0, 0, you will hit other rational points, integer point. And if the slope is irrational and you start at 0, then you will never hit again an integer point. Okay. So this is what happens on the next slide. So here I just change a little bit the slope alpha to be some irrational number, just a little bit bigger than the previous. So this will never hit again something. And in this case, the formula are the same. And then we call them, or I would call them the upper characteristic Sturmian word, and the other one using the floor, the lower characteristic Sturmian word. So these two configurations differ in this case only at the origin at two positions, so at position -1 and at position 0, where a flip occurs, like 1, 0 becomes 0, 1. So if you look at the literature, like in the 90s, in Berstel, sometimes they use, when they say Sturmian, they include the periodic case, but more lately, like in the books in the 2000 and Lothar, they will, like, Sturmian will be most of the time will be assuming that it's not ultimately periodic, and this is what I assume here. So this is why I say this is a Sturmian case when the slope is irrational. So now I want to come back to the case where the slope is irrational. So in this case, of course, as we have seen on the 2 slides before, the configuration becomes periodic, right? The mechanical word, the upper and the lower mechanical words becomes periodic. So here on the picture, you see also that I'm making a shear. Okay, I'm applying a shear matrix so that now the vertical steps are really vertical and the horizontal step, they stay horizontal. So this is the same picture as before, but just applying this matrix. So here, the period that you see, the primitive word which describes the period, the smallest period, allows to give a definition of what is a Christoffel word. So in this case, let me also introduce notation at the same time. So our two lower and upper mechanical words are periodic. And if I start at 0, the lower mechanical word is some word W here, which repeats. And this W, actually, this is exactly the lower Christoffel word of slope P over Q. So this is if you write, because of the shear matrix, if you write the slope alpha to be P over P plus Q, where PQ, this is a mistake, AB, it must be PQ, where PQ are coprime integer. And of course, W prime is the upper Christoffel word. So the difference between the lower and the upper Christoffel word is very small because the middle part is the same. The blue part here is the same. So this is called the central word. And only the last letter change. So 1, 0 for the W prime and 0, 1 for the lower Christoffel word. And, the fact that W here stays always below the segment, this makes the unique among its conjugacy class, the set of conjugate of the word W, which is obtained by shifting the period. And this is equivalent to say that, in fact, it is the minimum for the lexicographic order among all the conjugate of W. So in other words, the W is the lower Christoffel word is a Linden word. And similarly, W prime is the maximum among all its conjugates. And there's no notion of Nilden or Linden corresponding to that. It's just the maximum. It's a primitive and maximum among its conjugate for the lexicographic order. Okay. So this is it for this slide. Yes, let's go next. So let me recall the books where these notions are defined and many more result. For instance, relating Sturmian sequences and Christoffel work with constant fraction expansion. So for instance, the chapter 2 of the Lothar book, which was written by Bercel and Seobol, is on the topic of Sturmian sequences. Similarly, the chapter 6 of the PTS Fogg book, which was written by Pierre Arnoux, only the chapter 6, written by Pierre Arnoux, is considers also the Sturmian sequences with a different angle, more dynamics, and closely related to induction of like the rotation of the circle and so on. Chapter 9 of the Alush and Chalet book also considers the Sturmian sequences, and in that case, the title of the chapter is characteristic words, which corresponds to Sturmian sequences starting at the origin, really, which is what we have seen just in the previous slides. And also, I would like to mention this more recent book by Christoph Rothenauer, which contains like almost, well, all, but I would say all of the results, because maybe there's new things to learn about Christoffel, but a lot of the results among Christoffel words are listed in that book. It's a very nice book to look at, including what is called the Pirillo's theorem, which is on the next slide. So Pirillo's theorem, it's a nice result which appears in 2001, which gives a characterization for Christoffel word. So take W equals 0 M1 and W prime equal 1 M0 for some word M. So Pirillo's theorem says the word W is a lower Christoffel word if and only if W and W prime are conjugate. This is a very nice result. I like this result very much. And here I have shown an illustration of this theorem. So here we see the lower Christoffel word with the green shaded region. So what the theorem says is, in fact, you can see the lower Christoffel word as a shift of the upper one. And in fact, it appears here. Okay. The position here, I don't know if you see my mouse. I'm moving the mouse on the screen. Hopefully you see it.
Yes.
Yes, we can see it.
Okay, so this position is where the shift happens. Okay, where the position where you see the lower finish here. So what is this point? So this point corresponds exactly to here to the point where which is the closest to the line. So this corresponds to the standard factorization of Christoffel words. So there's a unique such point. So this point is here, and it corresponds to something also which is nice, which is the factorization of the Christoffel word into two palindrome. So this is also unique, and this point corresponds to that because so the lower and the upper Christoffel word are a product of two palindrome, and if you exchange those two palindromes, you get from the lower to the upper, because you see that 0 1 0 0 0 1 0 1, this is a palindrome, and this part as well is a palindrome, and if you exchange those two, well, you get you go from one to the other. Anyway, so this is a very nice result. And in a work with Christoph Rothenauer, we in fact use that theorem to try to extend Christoffel words in higher dimension. Just using this idea of you flip at one place and you are shift, so what can you be? You must be some Christoffel graph. And in this case, we generalize words to graph. And more recently, I realized maybe it was a mistake because it's not really graph that we want, but it's really just a surface of faces anyway. But we can still state it as graph and get a result. So now there's another question I want to suggest it is the next slide. So this theorem is very nice. It allows to give a characterization of Christoffel word, but could it be used to also give a characterization to Sturmian sequences? This is a question I have in mind, which is the next slide. So here let me explain. Okay, so this slide, for now, I go step by step. So I want to go from words that are finite, from W, it's a finite word, to infinite word. Okay, so I would like to transform this theorem into a theorem for Sturmian sequences. But for now, let's make it B infinite, go from W to B infinite sequences, which are periodic. Okay. So this is this statement. So this is just Pirillo's theorem, but restated for periodic B infinite sequences with period W. So if we restate the Pirillo's theorem, we could state it this way. So W, the B infinite word W with period W, is the lower mechanical word of slope alpha if and only if W, the periodic configuration with W, is a shift of the periodic W prime. This is just a restating, like the fact of being conjugate here just means that the two B infinite sequences or the two B infinite configuration are a shift of one another. Okay. So this theorem works. Okay, we can state it like that. And then one thing you can ask is sorry. Now consider alpha, a slope, which is irrational, and consider this theorem, and you want to take the limit of a sequence of P over P plus Q of slope, of rational slope, going towards irrational slope. And you would like the statement to survive. So does the limit of Pirillo's theorem when the slope goes to an irrational exist? So that's the question I ask. And the answer is, in fact, if it's stated like this, is no. Because we are lucky that when it's periodic, W is a shift of W prime. It's a conjugate of W prime, but at the limit, this does not hold because the shift each time when you go towards a irrational, so the shift is greater and greater and greater. So at the limit, when you get to really the Sturmian sequences, C alpha and C alpha prime, then one is not a shift of the other one. Otherwise, it would become ultimately periodic. So the limit is not defined. So there's no that's not to this question, the answer is no. But maybe there is another way to change the fact of being conjugate. So we need like a weaker notion of being conjugate because this is kind of too strong to ask, to have something similar that will give a characterization of Sturmian sequences. But from this point, this is a question I was wondering a few years ago, but I had no idea how to make this work. But then Sébastien came with something, and we'll see. So now I will just, we are in the part where I will introduce the terminology, or maybe I will start with terminology that you know. So let me recall if necessary. So we consider in this talk a finite set that I will denote by sigma. So this is my alphabet. Over this alphabet, I consider the space of all configuration, so B infinite sequences. So I denote this set like that. So it's a set of configurations, so map from Z to the alphabet. So I endow the space of configuration with the pro-discrete topology. So you can click here, you get to the Wikipedia for the definition. So this is the discrete, the product topology where the projection on each copy of the alphabet is discrete. You want this to be discrete topology. So you want the preimage of all of these to be open set, etc. So if you look and you understand, the exercise on topology, you understand that in fact what we want is that if we have two configuration X and Y, and suppose they agree on a large ball around the origin, so I denote the origin here with a dot like this, then these two objects are close in the topology. Okay, the distance between X and Y is close to zero. So the larger the ball, the closer to zero the distance. Okay, so now to a pattern P. So it's a map from S to the alphabet with finite support S. So it can be contiguous to get a factor or not. This does not matter. So let me recall that we call a cylinder, so the set of configuration such that when I look at the subset, the support S, I see the pattern P. Okay, so I will denote this set of configuration as with the square around the pattern P. Okay, so this is a subset of the space of configuration. And then on my space of configuration, I consider the shift. Okay, so the shift, I suppose I have a configuration X, I shift it to the left. Okay, my shift moves the configuration to the left. And it's invertible because I'm considering my configuration to be B infinite. So I can always shift them back by shifting to the right. So then I will denote this by sigma -1, okay? Then in the space of configuration, you may have two configurations, X and Y, that look the same, in fact, that are the same everywhere except on a finite set, okay? So for instance, X and Y here, they agree everywhere except at position -4, so -3, -2, -1. So this my 0 here denotes that this is position 0, right? My position 0. And then 1, 2, 3, 4, they are different. 5, 6 is the same. And then 7, 8, different. Okay, so I put square box in all the next slides. It's like this also, around stuff that are not the same. Okay, so in this case, I will say that X and Y are asymptotic. This is a notion which exists in the literature. So in some sense, when X and Y are asymptotic, it means you can shift them. So you want the shift to be, you want to shift to the infinity, and this goes towards 0. So if you shift this to the infinity at the left or at the right, then this will get arbitrarily close to 0. The sigma n of y, sigma n of x will get closer and closer as n increase. So, but here the definition, so let me read it because I said it, but X and Y two configuration are asymptotic if X and Y differ in finitely many sides of Z. And then the set F where the two configurations are distinct, I call this the different set. So the set of position where the two configurations are different, the different set of X and Y. Okay? Then here I want to introduce the notion of pattern discrepancy. So now we said we have two asymptotic, we assume we have two asymptotic configuration X and Y with different set F. And then I choose some pattern P with finite support S. And then my goal is I want to compare the number of occurrences of the pattern P in X and Y. So like, I want to do this. So this is a notation which is often used for finite words. So if X and Y were finite words, I would like to compute the number of occurrences of P in Y minus the number of occurrences of P in X. So this is what I want to do in this slide. Of course, if X and Y are infinite, maybe the pattern P occurs infinitely many times in Y and infinitely many times in X. So this is for infinite configuration, this is infinity minus infinity. So it's not so well defined here, okay? So I want to make this formal so that this is well defined. So this is what we will do. So let's start with an example, because when we have two asymptotic configuration, and we can do it, okay? There's a way to define it. So for example, so consider the pattern 1001 with support 0, 1, 2, 3. So here my pattern, you see, it's not a factor, right? It's a real pattern which is embedded in space at position 0, 1, 2, 3. So we have to keep this in mind. So I underline or overline the position of this pattern, the occurrences of this pattern in X. So it appears here, 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 here. Okay, 1, 2, 3, 5 occurrences. And in Y also I have 5 occurrences. So of course, since X and Y are asymptotic, when the pattern occurs on the part on the left, where it's the same as in Y, then the occurrence here corresponds to an occurrence here. So if I want to make a difference, I don't need to compute them in some way. So that's what we will do. So this occurrence corresponds to this one. On the right, we have one occurrence here, which is here, one occurrence here, which is here. And what we really want to compare in the end is the number of occurrences that overlaps, whose support overlaps the different set. So here we have one occurrence here in X, so 1, 0, 0, 1. And in Y, there's one here, 1, 0, 0, 1, yes. So this is why when we define what we call the pattern discrepancy, so the P discrepancy associated to the asymptotic pair XY, we compute it like this, in fact. So what we want to do logically is to make the sum goes over all integer n, all shift. You know, that's what we want to do. But but since it's not necessary to compare the position where the support is outside of f, we can restrict the sum, in fact, to the difference of f minus s. And what we will do, so let me explain the notation here. So this is the characteristic function for the cylinder P. And here, instead of moving the pattern P, I'm moving the configuration. Somehow it's the same. So recall that sigma n shift to the left. So it means that if like this part will be equal to 1 if and only if pattern P occurs at position n in Y. Because this sigma n of Y shift the position n at position 0, and then this, with respect to 0, you look at whether P appears, okay? And then you make the difference with the same thing with X. So each time I need to take a few seconds to understand that this is really what we want to do, and this is the note I wrote here that helps me to make sure that the sum does what we want. So if n is not in f minus s, meaning if it's in the integer but not in the difference of f minus s, well, this is equivalent to say that n plus s intersection f is empty, which means that in fact our shifted support does not intersect the difference, which is exactly what we want to remove from the sum so that it becomes finite and well-defined. Okay. So this is the pattern discrepancy. Then with this we can define what we decided to call indistinguishable asymptotic pairs. So we say if we say that two asymptotic configurations are indistinguishable if the pattern discrepancy for each pattern is 0. So indistinguishable, it means if I give you only the statistics, you will not be able to distinguish X and Y. So let me do some examples. So example 1, the trivial asymptotic pair XX is indistinguishable because the sum is over a fine empty set because F is empty in this case. So we do keep the trivial asymptotic pair as allowed to be defined as indistinguishable. So the example 2 is, so this was, well, Sébastien Labbé was like, of course this works, yes, but in fact, it's showing that, for example, 2, it satisfies the definition. It's already a good exercise, I would say. So here, you take the configuration, the sunny side up sequence, sometimes it's called like this. So you have only one at one position and all zeros everywhere. So you shift it by, in this case, 7 or something, and to get Y. So these two will be indistinguishable. So let's try to understand why. So if you take a pattern P, which contains the 1 here, then you will have only one occurrence in X and 1 in Y. So 1 minus 1, 0. So it's okay. So what is more to me difficult to make sure it works is if you don't have a 1 in your pattern. So you take a subset where only zeros appear, and you want to make sure that you see the same number of such occurrence of such pattern in both. So it's not so easy, but it works. Okay. To make the proof that it works, it's better to wait for the theorem, and then we'll come back to it if you want. So in both of these two examples, the X and Y lie in the same orbit. So question, can we find other example? Yes, that's what makes it interesting. So before more interesting example, let me give a non-example just to show you also that it's not because X is a shift of Y that it works. Okay, so for instance, if you take all zeros, then all 1, and you shift it to get Y, then these are not indistinguishable. This pair is not, because in fact, in the different set, you need the same number of occurrences of each letter. Because here, if you take as a pattern, you take the letters, the definition of indistinguishability says you need the same number of occurrences of that letter in the different set. So here, we have 7, 1, and here 7, 0, so it does not work. If you compute this for 1, for instance, you get -7. So this is not indistinguishable. Okay. So in example 4, we see that in the different set we see ABC, and here in the different set we see BCA. So already this is good because the pattern discrepancy for A, B, and C is 0. Okay, so now we can look at the words of size 2, words of size 3, and so on. So let us make the exercise for words of size 2. So if you look at words of size 2, so of course you only factors of size 2, you only need to look at those that intersect the different set, right? So there's not a lot of them. You have CA, AB, BC, and CB. And if each of them, CA is here, AB is here, BC is here, and CB is here. So it works. So this, for all factors of size 2, the pattern discrepancy is 0. So maybe we can look at 3 and so on. So here, the example I'm taking is ABC, ABC. So in this case, I underline the occurrences, and we see that it also works, in fact, because the pattern discrepancy for this pattern is 0. So in this case, you see that this is a, I don't tell you how I constructed it yet, but it shows that you can have indistinguishable asymptotic pair for alphabet not larger than 2 of size, or ternary alphabet and so on, or larger also. Okay, so now I can state the theorem, no secret. In fact, if you have X and Y, so here on the binary alphabet, 2 configuration, and now let's for now assume that X is recurrent. So the pair X and Y, we showed this. So we show that the pair X and Y is an indistinguishable asymptotic pair with different set -1, 0, such that, let's say, for X it's 1, 0, and for Y it's 0, 1. So this holds if and only if there exists an irrational number between 0 and 1, such that X and Y are exactly the lower and the upper characteristic Sturmian word of slope alpha. So this is, to me, is very interesting, because when we came up with this definition, which was brought by Sébastien Labbé, I will show at the last slide of the talk where this notion of discrepancy comes from. But when Sébastien Labbé gave us this question, it was not clear at all that we were obtaining Sturmian sequences. Everyone was telling me, it must be another fun and Wolf theorem, only periodic configuration happens, satisfied. But in the end, no, you can have a periodic, and these are exactly the Sturmian when the difference is of size 2, of course. So now I will give you, I guess, the idea of the proof. Yes. So I like the way the notion is placed, let's say, in the proof. So recall here that we assume that X is recurrent. Okay, so the mechanical words. So it's well known that mechanical words, that's the result, which is in the Lothar, but it was proved by Morse Hedlund at the beginning, like the link between mechanical words and balance sequences. And later on, Coven and Lund made the link also with sequences having of complexity n+1. So the equivalence between mechanical words and sequences of complexity n+1 is known. So the notion of indistinguishability, it comes in between this triangle. So of course, let me say something else. So when you want to do the proof of mechanical words, the equivalence between mechanical words and complexity n+1, there is one direction which is easy. The easy direction is to show that the complexity is n+1. This is a few lines. What is difficult, of course, is to show if you have a sequence of complexity n+1, then this is a mechanical word starting with this starting point, with this slope, because the slope is related to the development and the constant fraction expansion, and the starting point is written in the Ostrowski numeration system. So you need to introduce a lot of a form of definition to make the proof. But this The other direction is easy. So the indistinguishability, what I want to say that is in between the two notions in the easy part, in fact, of the proof. So when you show that mechanical words or coding of irrational rotation of complexity n+1, in fact, the kind of proof you do is you make this drawing and you show that depending on where the starting point is, well, this is exactly the words that you will see of size 4, let's say. So it partitioned the circle according to the starting position, depending on where it is, what you will see, what you will code in the sequence. And so, of course, if you separate a circle like this by, at the start, there are two letters of size 1. And each time, if you have one separation, you increase the complexity by 1 at each step. So the proof is something like this. So in distinguishability, we can show this instead. So how do we do it? In fact, we need to know what are the intervals here, so the cylinders here corresponding to each word when you look at the lower and versus the upper mechanical word. So in this particular, for these two configurations, which are very particular, the starting point is at 0. And depending on you use the floor or the seal, this interval will be left closed, right open, or left open, right closed. So this change makes the difference on what happens if you start from 0. And this is important. So if you start at 0, you need to go back for some reason. So you go back by minus alpha, minus 2 alpha, minus 3 alpha, minus 4 alpha. So exactly, so this gives you exactly the words you see at this position. And depending on whether your intervals are left close or right close, then you will fall in each of the 5 interval here, but in different order. But in any case, if you take around the different set, you will see the same 5 words of size 4 overlapping the different set exactly once. Anyway, so this shows that it's indistinguishable because each factor of size 4 appears exactly once intersecting the different set. And then if now you assume that you have x and y that are indistinguishable, in fact, you can show the proposition which is here in general for a general different set. So there are few lemmas that come before that you can show that you can always, for any factor occurring very far in the sequence, you can always bring it back closer. So I could try to explain this so that it intersects the different set. And because of that, you can show that an upper bound for the language, the complexity of the language, it has to be bounded by the number of of ways of intersecting the words of size 1 with the different set. So if the different set is of size 3, you have maybe like this, exactly n plus the size of f minus 1. So if the size of f is 2, then you have at most n plus 2 minus 1. So this, in the case where the different set is of size 2, it gives right away that the complexity has to be n plus 1. So the proof is not so difficult in this case. And if you want more details on the lemma, I will write for a question. I will continue for now. So now let me give you an example with Christoffel words, because it allows to see what's happening with the combinatorics. So if you take any Christoffel words of slope PQ, 0 m1, so the words is of size n, and then you concatenate 0 m1 with let's say 1 m1 on the left, and you take, in this case, 1 m0 with 1 m1. Okay, so you take those two words of size 2n, and so this has, if you slide a window of size n instead of those words of 2n, you see n plus 1. There are n plus 1 position for the window, and it turns out that all those n plus 1 words are different. And you can see it using a computation in Sage. You define u, you define v, you compute the set of factor in v of size 13 in this case, and the set of factors size 13 in U, and they are the same. And then you compute the size, of course, of those set, and it's 14. So confirming that all of the 14 words are different. And just to make a link with last week talk, because the notion of binomial coefficient was used, because those two words, like combinatorial, are kind of similar because they have the same factor. Two words different, but the same factor of size 13. But if, of course, since you obtain one from the other by flipping a 0 with a 1 0 by a 0 1, you change the number of subword of size of 0 1. So here I compute this. They are not binomially equivalent in that sense, but they are close or indistinguishable for a notion if we define it for finite words. Okay, so now I want to present the theorem B. I will need to accelerate. Sorry, just check the time. Okay, so theorem B. So now I remove the recurrence from the hypothesis. And what do I get? I get that the pair XY, the asymptotic pair, is an indistinguishable asymptotic pair with difference set -1, 0. So the same thing. If and only if, in this case, there exists a monotone sequence of irrational number alpha n, such that X and Y are the limit of characteristic Sturmian word of slope alpha n. So this is interesting. So you take a sequence of characteristic Sturmian sequences towards a rational slope. And of course, the limit slope must exist in this case. So you do have an alpha, which is the limit of the alpha n, which can be rational. And this is exactly what are the indistinguishable asymptotic pair. And this is very interesting because at the limit, when you go towards the rational, you don't get a periodic sequence. You get ultimately periodic sequence, but it's not periodic. So it gives really to me, this is very a nice result, which describe what are indistinguishable asymptotic pair, but in some sense also it explains what should be like a Sturmian sequence at the limit. So I like this result. I like this statement anyway. So what do you get when you consider a limit towards a rational slope? So this here explains it. In fact, you obtain the Christoffel word, but not exactly the same period on. The word itself is not purely periodic. On the left, for instance, if you take at this one, on the right you get 0, m, 1, infinity, and on the left 1, m, 0, infinity. Of course, this is a conjugate of this, so you can say that it's the same period, but in between there's some flipping that happens. You go from one period to the other. So this depends on whether you approximate the rational number from above or from below. And of course, there are the limit cases which you need to consider differently when the slope is 0 or 1. Okay. And okay, so there's a lot of text here. So there's one thing I would like to show if I have the time a little. So in the proof, so of course, if X is recurrent, it corresponds to the theorem A, because if X is recurrent, the sequence of Sturmian sequences goes towards Sturmian sequences, usual Sturmian sequences. So when X is not recurrent, you can show that you must have X and Y. In fact, you can show that X must be a shift of Y, because since it's not a recurrent, it means there's a factor that happens only a finite number of times. So you can take a factor which englobes all of that. So that factor will occur only once in X and Y, meaning that in fact you need this forces X and Y to be shifted. So suppose the shift is K, and assume here for now that the K is larger than 2. So there must exist some M of size K minus 2, which goes in between here in the hole. And what do you get? Assuming it's indistinguishable, what I want to show here is like you have the M, the 1M0, which intersect the different set. So you must see this factor 1M0 inside the intersecting the different sets in X. So then you must have 1M0 is a factor of 1M10M1. but certainly not as a prefix. So it means 1m0 is a factor of m10, m1. So then you can put back the letter 0 here if you wish. And this is exactly the square of 0m1. So when you have u is a factor of v squared and u and v are the same length, then it's equivalent to say that u and v are conjugate. So then we have m10 is conjugate to 0m1. And now we can use Pirillo's theorem to conclude that 0m1 must be lower Christoffel word. So just this part I like very much, because in the end the Pirillo's theorem comes involved in the proof to prove it in the case where we go towards the rational slope. Okay. I will state theorem C now. So now theorem A was with hypothesis, so recurrence and binary alphabet. Theorem B, we remove recurrence, but we keep binary alphabet. Now we take an arbitrary alphabet. So let sigma be a finite alphabet and x, y be a non-trivial asymptotic pair. Then we prove that x, y are indistinguishable if and only if two cases occur. So if x is recurrent, then there exists alpha, an irrational number, and a substitution, and some shift integer m, such that x and y are the shifted of the image under the substitution phi of the lower and upper characteristic Sturmian sequences. So here the shift by one is you need to move the different set on the positive quadrant, because the substitution, if it maps 0 and 1 on this, alphabet on words of different size, if the morphism is not uniform, it does not work. So you need to shift the 0, 1 and the 1, 0 in the positive part, so that the image under the substitution keep being asymptotic. So this is just a small issue here. So, but basically these are shift of coding of characteristic Sturmian sequences. And if it's not recurrent, in fact, you can show that they are shift of image of the very basic example where you have only 1 and just 0. 1, 1 and only zeros that you shift by 1. Okay, so how do we prove theorem C? I will go a little bit faster. So how do you prove that? Well, first thing you need to show is that if you have a substitution, then it preserves indistinguishability. So this is not so difficult to show. So if you have xy indistinguishable, then their image is also indistinguishable. And here I put an example, but okay, you need to work a little, but it works. I want to spend more time on the other part, so that's why I will accelerate here. So the other direction in the proof is very interesting. So, and it's using the notion of derived sequences, so which is well known also in the from the paper of Fabien Durand, but maybe he was not the first of doing this. But so assume A is a letter in sigma appearing with bounded gaps. So this A occurs like that, and you consider the derived sequence of X with respect to the return words to the letter A. Then we can show that the derived sequence also preserve the indistinguishability. So let me do an example here. So if you look at the sequence X and Y, we look at the return words to letter C. So the return words is, in fact, you look at the occurrences of the letter C and you make blocks like that, where you separate before the occurrences of the letter C. And this, you see that CAB, so this is one block, and then CB, this is the second block, CAB, C, yes, so CAB is a block. So you do this, you separate before each C here, and you see, in fact, the return words are only two, CAB and CB. So now you replace CAB by some letter, like for instance 0, and you replace CB by 1. And doing so, we obtain what is called the derived sequences. And we obtain this, and it's because of this lemma, the derived sequences here are still indistinguishable, and we see it on the example. But more importantly, you see that what happened on the size of the difference set, the size of differences reduce. It's now smaller. So you can do this step by step. until you reach a difference set of size 2, which is consecutive. And this, in this case, we have shown in Theorem A and Theorem B that it has to be Sturmian sequences or limit of Sturmian sequences towards a rational. So by going backward, then you prove the Theorem C, in fact, using the notion of derived sequences. So I'm almost done. Okay, so now I want to make this slide about the motivation. So where this came from, okay, so it was from this paper, which you can see on the archive of Sébastien Labbé with many co-authors, where, so this is in thermodynamics and Gibbs theory. So I don't know all of the vocabulary they use and so on. I would need to learn more. Each time I ask Sébastien to tell me and I forget. At some point, maybe I will learn, but let me at least say some word. So in this paper, so they were trying to answer a question, I think by Sullivan, and they answered negatively to the question. And to prove the counterexample, they needed to introduce some norm. So in this case, it's this norm. So there are two norms. This norm is the dual to the other one. And NS stands for non-solvable, I think. So if you have two x, y that are two asymptotic configuration, they define this. The norm is given by the sum or the sup over the sum 1 over s, the sum of the absolute value of the pattern discrepancy. So in their paper, to provide a counterexample, they needed to find an example of asymptotic configuration or a sequence of asymptotic configuration such that this norm, this value for this norm was very low, and to provide a counterexample. But in their paper, in the end, they did not need that norm to be equal to 0, just something very low. So at some point, they had in mind that we need to describe exactly what happens when this norm is 0, which corresponds to indistinguishable pair. But in the end, no, they did not need it to complete their paper. Anyhow, that question came at the end. So what are the asymptotic configurations such that this norm is 0? Okay, and this is what we call in our paper indistinguishable pairs. And surprisingly, this corresponds, it's very closely related to Sturmian sequences. So to finish, just to say that we are currently working to extend Theorem A from Z to ZD. It's much more work, but it's we are able to do it. Hopefully we'll finish this soon. But for now, extending Theorem B and Theorem C to ZD is more difficult. So Theorem C, somehow you need to, to define what are derived sequences in higher dimension, and this is, the shape doesn't keep rectangle. So because of the shape, it's difficult to define. And Theorem B, when you go towards, because now you have a normal vector which has many coefficients, and when this goes towards maybe this is totally irrational, but when this sequence goes towards a rational slope, there are many ways of doing this. So when in Z you have a sequence of irrational going to a rational, then it has to be either from above or from below. It's kind of easy, and it's easy to define what are the possible cases. But in higher dimension, it's much more difficult. So the approach of explaining all the cases is not so much doable. So we need to think more to be able to generalize Theorem B. Okay, I'm looking at the time now. So thank you. I went further a little bit, but thank you for your attention. I am done presenting the slides.
Thank you, Sébastien, for this nice talk. We have time for questions. Are there any? The audience? If not, I have a question. Do you think this new characterization can be used for something else regarding Sturmian words? Do you think you can use it to do something else?
As an application or as a... Yes, I'm wondering. It's a good question. So we need to to wonder what is the, like, being indistinguishable, like this notion, the fact that they have the same number of occurrences of each factor. I think that's what we need to think about. Maybe this notion already appeared somehow, or maybe, and well, I think because another way of looking at this is to say, the Sturmian sequences it's basically cut and project set of codimension 1, okay? When you look at this in higher dimension, this will kind of stay again. So it means if you take a lot of atoms in the space, and now maybe the atoms are not on a lattice, okay? The notion of indistinguishability can be defined outside of a lattice. You take a set of points or colored point, maybe in RD, and you can define the same. Maybe you have an asymptotic pair, and you say, suppose for each patch or finite region of the space, I see the same number of occurrences of each pattern in both. Anyway, then the result can be stated that, well, these are kind of quasi-crystals in the sense they can be expressed as a cut and project set of codimension 1. I don't know, maybe it has such kind of application.
Okay.
This is the idea I have in mind for now, but maybe there are other answer, but I don't have for now.
Okay, thank you. Any other questions, remarks, Sébastien?
Can I ask a quick question?
Of course.
I may have missed it, but I was just wondering how the notion of indistinguishability compares with the local indistinguishability notion, which means that any factor of one occurs in the other, any finite.
Okay, without considering the number of occurrences.
So is it stronger?
Sorry, so I don't know the other notion you speak about. So I just want to.
Local indistinguishability essentially means that any finite factor of one word occurs in the other and vice versa.
Oh, okay. So the same language is somehow.
Same language, yeah.
Yeah.
So essentially, one is in the closure of the translates of the other, or something.
Yes. So it's a good question, and that we considered, and Sébastien Barbieri provided an example which answers that, and it gives the importance of the notion of indistinguishability with the way we define it. And there is an example in the archive paper based on toplet sequences, where it provides an example of a pair of asymptotic pair with the same language that are indistinguishable. That have the same language, but they are not Sturmian sequences. So there is a counterexample.
Okay.
So I'm curious, the notion of
interesting, yeah, to see how they kind of relate or not. Yeah.
So can you? But it's funny because we use the notion of indistinguishability, like this word. We choose this word, but we didn't know about I didn't know about the local indistinguishability notion. So it's kind of by coincidence that the same word is used for both. So
it's a pretty natural word for this kind of question.
Yes, but at some point in time, that was not the word we were using.
Yeah.
So
we tend to just call it LI because that is so much quicker than local indistinguishability. Okay, and some people use local isomorphism or something like that. So there are different notions, even with the same abbreviation around.
Okay. So I will look in the literature, but I will, if I don't find, I will.
But it's clearly a different definition if there is an example which has the same language but still is.
Yes, but I'm still curious to read the paper that use that definitions. If I don't find, I will write to you a question.
No worries. No worries.
Give me the...
Thanks. Nice talk, by the way.
Okay, thank you.
All right, thank you. Well, maybe we can end questions here and turn to Jeff. I think Jeff has something to say.
Sébastien, could I ask you to please unshare your slides?